Okay, good morning. This is a quick review of circuits for you guys who didn't have it in Physics 1 last year. I'll be pretty quick, but you can stop the video and take down notes and record things and listen to it twice if you're so inclined. This is chapter 17 and 18 in your textbook, so it's going to talk about DC circuits. DC circuits are created when you have a pathway for electrons called a circuit, so you need some components hooked up and allow the electrons to flow through. This is obviously inside your house. You have circuits running through everywhere. Now, the key components to any circuit is they have to have a voltage source. We talked about that last chapter, typically a battery. You have to have a complete pathway. In other words, there can't be a break in the path. It has to be complete. And then you have components along the way. In this case, a light bulb, but it could be a capacitor, it could be a resistor, it could be anything in a computer, for example. We talk about voltage. Voltage provides the push to the electrons. It really provides the E field that pushes the electrons through the circuit. And of course, the units are volts. Current is the actual flow of the electrons. The symbol for current is capital I, and the units are amps or amperes. And so remember, inside a wire, if you just have a bunch of charges sitting there and there's no electric field, the charges aren't doing anything. The electrons aren't doing anything. But as soon as you put an electric field in there, inside the wire, the conductor, the electrons will flow, in that case, against the field, but the field causes them to move, and that movement of current is called current. And finally, the last thing we typically have in a circuit is something called resistance. The wire does not allow the electrons to flow unimpeded, and so this impedance or resistance to the flow is called resistance. In physics, resistance is given the symbol capital R, and the units are called ohms. I always liken this to freshmen in the hallway. If you're the current trying to get through the hallway and there's freshmen in the hallway, they provide the resistance to block your flow or your current. This is something that's kind of AP-esque. If there's something called Ohm's law, V equals IR, so the voltage equals the current times the resistance. If this is a linear function, if it turns out to be exactly linear, we say it's ohmic because it obeys Ohm's law. Some things are not ohmic. So in the AP test, they may say to you, is it ohmic? And what they mean is, does it follow Ohm's law, V equals IR? We'll talk much more about this later. Just really quickly about what affects the resistance of a wire. This is super obvious. The resistance of a wire depends on what the wire is made out of, its resistivity, how long the wire is. So a longer wire has more resistance, and how big the area is. So if the area is large, if the area of the pathway is large, then resistance goes down. So again, just think about the hallway. If the kids are blocking the hall and it's wide, you can go around them. If it's narrow, you can't. So that's a memorized formula. It's also a function of temperature. Resistance and temperature are related to each other. So as the temperature of something goes up, the resistance goes up. So we have some materials that are superconductors, and they don't have very much resistance. They have to be super chilled, have to be very, very cold. So again, a basic circuit has to have a voltage source, a pathway, and some sort of load. And as long as the circuit's closed, the electrons will flow. If the circuit's open, then the electrons don't flow. We talked about this a little bit the other day. There are two types of current. One is called alternating current, and it means the current goes up and down. It changes as a function of time. So the current in your house is AC. It starts off as 0. The current flows one direction, and then the current turns around and starts flowing the other direction. So it alternates back and forth. And that's typically most things in your house are, or at least the current coming through your outlets in your house is AC. DC is what we are most familiar with. Almost everything we have runs on DC. So your iPhone runs on DC, your computer runs on DC. And that just means the voltage and the current stay constant. It's there or it's not there. Inside a circuit, we have the actual physical things. We have a battery, a switch, a light bulb, and a resistor. In circuit diagrams, it's a lot easier to draw in certain ways. So this is the symbol for a battery, a positive terminal, a negative terminal. We also call the negative terminal ground. It's where the voltage is 0. The other side, the voltage is, let's say, 1.5 volts. A switch, and resistors. So these are the symbols we use. This is kind of key. When you're using a voltmeter, voltmeters measure change in voltage, and therefore they have to be hooked up in a circuit a certain way. We say in parallel. So we have to put one terminal of the voltmeter on one side of a component, put the other terminal of the voltmeter on the other side of the component, and it measures the difference in the voltage. We'll see this in a little bit. Ammeters are the opposite. Because ammeters measure current, we actually have to put the ammeter in the circuit, in line. We have to break the circuit open, put the ammeter in there, so the current actually flows through the ammeter. And again, we'll see this. Now, you can go online and visit FET. They have a circuit builder, and that's actually a good idea to sort of play around, see how things work. Now, this is a big thing. Ohm's law is by far the most important law that we use in this unit. There's two ways of expressing Ohm's law. One way is saying the change in voltage across a battery or across a resistor, across some component, is equal to the current flowing through that component and the resistance of that component. So V equals IR. That's the typical way of doing it. So if I want to find out how much the voltage drops, for example, if I run 5 amps through a 2 ohm resistor, the voltage will drop by 10 volts. This is also helpful if we can use the same law. Sometimes we want to know how much current went down a branch, so how much current is in a particular part of a circuit. We need to know how much did the voltage change and what the resistance was that caused that change. And again, this is a little confusing when you first do it, but after you play around with it, it's basically using this law in this form or in this form. Now, this is the other thing that's kind of important to remember, and kids say this incorrectly all the time. So voltage, remember, we think of voltage as a height. So when a current flows through a resistor, the voltage drops. So anytime you have current going through a resistor, the voltage will drop. It will go from some number down to a different number. Voltage does not flow. Current is what's flowing. So the electrons can flow. And just like cars on the highway can flow and take different pathways, electrons can arrive at a junction and fork different directions. So kids always ask us, say, how much voltage flows down branch 1? That's like saying, you know, how many squirrels do calculus? It makes no sense. So you think about current flowing. Current can go down one branch or the other branch, but the voltage does not split. And again, what I just showed you is if you want to use Ohm's law, you can use it to say, I can figure out how much the voltage drops if I know how much current went through a resistor. So that's one way we use it, is find the voltage drop across a resistor. And we'll see examples of that. The other way is if we have a circuit, for example, if we have a branch here in a circuit, and we know the voltage up here is 10 volts, and we know the voltage down here is 4 volts, and we know this is 3 ohms, we can figure out how much current is actually going down that branch by saying the current equals the change in the voltage, all divided by the resistance in between. So the change in voltage, the voltage at the top, would be 10 volts. The voltage at the bottom would be 4 volts. So the voltage changed by 10 minus 4. The resistance in between was 3. So it would be 6 over 3. That means that 2 amps comes down this branch. So we can use Ohm's law 2 different ways to help us to calculate and sort of work our way through the puzzle. Circuits are very much like crossword puzzles. You sort of work around, figure out what you know, and proceed through it. Now, just like we talked about this with capacitors, there's two ways in which loads or resistors can be connected. A light bulb is just a resistor that happens to glow. So here we have a battery with a positive terminal. Let's say it's a 9-volt battery. The voltage at this terminal is 9 volts. The current flows, goes through the switch if it's closed, and then it goes through the resistors. Now in this case, we say it's a series circuit because there's only one pathway. Current flows through this light bulb, the current flows through this light bulb, the current flows through this light bulb, and comes back to the battery. As the current goes through each resistor, the voltage drops. So for example, if the voltage were 9 here, it goes through, there's a voltage drop. It may drop down by 3 volts down to 6. It drops by 3 more volts down to 3, and it drops by 3 more volts back to 0. So the actual voltage, the batteries drive voltage up, and resistors drop voltage down. And so it goes from its terminal voltage of 9 down to its other terminal voltage of 0 through 3 resistors. Resistors, these are in series, again, because there's one pathway, or you can say that all the current goes through each. Now, these are the rules. I'm not going to go through these. Just pause the video, jot down these notes. This is the key thing. The current everywhere in a series is the same. The voltage drops add up, and this is the key, and we saw this with capacitors. In series, capacitors had a different rule. In series, resistors simply add up. The total resistance is the sum of the individual resistors. So this is a key series of notes. I'll do some examples in class. Don't worry about getting this down. It's super easy. Parallel is the opposite. We talked about this with capacitors. Here we have not one branch, but separate pathways. Each resistor is on a separate path. So these are connected in parallel. And again, the word parallel does not talk anything about the geometry. It just talks about how these things are on separate paths. Don't worry about how it looks. It's really based on whether the current splits or not. And again, for the parallel, the rules are different. The voltage drop across each of these is the same. The current is actually the sum of the currents, and this is an important rule. You'll see this in a second. And then the resistance adds up, just like we have capacitors in series, resistors in parallel add up the same way. Just don't forget to do the 1/over part. A lot of kids forget to do the last step by inversing the RT. And again, we'll do some examples. I'm not going to do these on the board, but we'll do them in class today, tomorrow, next day before break. But you guys should look over this carefully and make sure all the examples make sense. Now, just like we have capacitors hooked up in series and parallel, we also can hook them up in combos, and it's kind of the same method. Here I have a bunch of resistors. Here's the battery down here. We have a resistor. It's in series, a bunch in parallel, then those branch in parallel. So there's a combo circuit. In the combo circuits, you have to do step by step. And again, there's some rules here. You can pause the video and sort of stop and look. But most kids learn how to do circuits just by doing circuits, and I'll give you guys a packet full of practice problems. We eventually will do circuits that are pretty complicated, but even this looks complicated. It's really not. And the AP will never ask you something that's complicated. We usually overteach you for the AP test. And again, I have problem sets, so we'll give a bunch of these problem sets out in class, and you can go through that. The last thing I'm just going to talk about briefly is something that was power. Power is what we call watts. So when you're working on at your house and you have a 40-watt bulb in your lamp, it's talking about how much energy per unit time is passing through. And there's 3 different ways of calculating power. One is to take the current to the resistor, square it, and multiply by the resistor. So in your house, you have a certain amount of current flowing through that light bulb, and that creates a certain amount of power. So more current or a higher resistance creates more power, makes the bulb brighter. You can also look at it as the voltage drop across that resistor times the current. Or we're just using Ohm's law to derive out these others. So I usually just memorize this one, and then I can derive the other 2. This has I and R, that has I and V, that has V and R. And you could I just memorize that one and then use the V equals IR to derive the other equations. And again, these are some power questions. We'll go over these in class. Again, you can stop. Now, like I said, on Thursday and Friday before Christmas, we'll do a bunch of packets. And I think the best thing for you guys to do is just do a bunch, and then you'll sort of get the hang of it. After you do series and parallel, then you can learn how to do combos, and it's very simple. So these are quizzes. There's some AP release problems you can take a look at. And then we take a quiz. And then we take a test. And eventually we'll do this after Christmas, so don't worry about that. So anyway, that was hopefully not too painful, but it's a basic idea, and you'll be fine.